Hello, in this video we will talk about energy in rotational motion. And, well, energy considerations. Let's consider another potato chip. So once again, I'm applying a force. We know a component of this force is going to be radial, like so. The other component will be tangential, like so. Okay, that will be the radial and the tangential component, right? So because there is a tangential, look, the radial component does nothing. This thing is fixed around this axis. So this thing can only rotate, rotational motion. So that the radial component of the force does nothing, but the tangential component is actually making this point move. So there is a displacement along the segment of arc here. So we can define work. There is a chunk of work done because there is a force, which is the tangential, but it doesn't matter. I want to do the dot product here with the chunk of the displacement, right? So we know the work is F. The component that does work is just the tangential, which is F sine of phi, as we see here. The phi is the direction, is the angle between the radius and the force. So F sine of phi times the radius, right? We know times delta theta. But this is exactly what we call torque. So the work done by the force is equal to the torque times delta theta, right? This is for angular motion. For linear, remember that the work was force and displacement. Well, now it's torque and angular displacement. If I divide this over time, what I get is power is torque and then angular velocity. Remember that power was not only energy over time or work over time in linear terms, but it was also force and velocity. So you see here we have torque, which is the angular equivalent of force, and angular velocity, which is the angular equivalent of linear velocity. There you go. So we have two equations, right? And the other one was the work is, right, well, there you go. Angular equivalent of work and power. So all you have to do is multiply whatever torque you have times the angular displacement or the angular velocity. What about the work kinetic energy theorem? If you have work in linear terms, translational terms, that was 1/2 mv squared, mv final square minus 1/2 mv initial square. What do you think is going to be the rotational equivalent of that? Well, same thing. Change in rotational kinetic energy, which is going to look like 1/2 I omega final square minus 1/2 I omega initial square. If you want to see the derivation of this, go to the book on page 269. I'm not doing it because we need integrals, and I know you have not seen integrals in calculus, so, but we see the analogy, right, between work kinetic linear or translational energy kinetic and work and rotational kinetic energy. Same thing. Which brings me to the following table here. This is rotational motion, this is translational motion. Of course, we have position It's not in this table, and displacement. This will be theta, this will be delta theta, here it will be x, and this will be delta x, right? But then we have, for every translational or linear motion, we have a rotational equivalent. Most of this we already went through in the videos. All of this is in the book. Speed, rotational, angular speed. Acceleration, angular acceleration. The equivalent of force is torque. Instead of mass, we have angular mass or angular inertia. All the kinematic equations have an angular equivalent. Same thing, work, you see they do the integral. Force displacement, here's torque, angular displacement. As we saw, for the kinetic energy, there is a rotational energy equivalent. Power is the same thing. And then this last two equations, this is the next chapter, but there is going to be an equivalent for linear momentum, mv, well, it's going to be I omega. And remember how the actual definition of force, according to Newton, the net force was a change in linear momentum with time. Well, now we eventually going to learn that there is that the net torque, angularly speaking, is the change in angular momentum over time. Right, this L is the angular equivalent of this P. Mass times speed, or actually mass times velocity, and then here is angular inertia, a moment of inertia times angular velocity. Okay. Now the concepts and the derivation of the equations are relatively easy, but doing problems involving these equations is not as easy or as straightforward. So in class, we're going to practice with all these energy equations in rotational dynamics.